Hi, with this video and this worksheet, we're thinking about what can I do once I have a mass spectrum, or how can I interpret that to understand more about my atoms, my elements, and specifically their average atomic mass. So right here, this is a mass spectrum for a sample of gold. So the abundance is the y-axis, how much of that isotope I have. The x-axis is the mass of those. And I've summarized what I have up here, and I'll make this a little bit bigger as we go through the math in a moment. But as we look at these numbers, 24, 77, and 39, they don't add up to 100, meaning that these are relative abundances, but these are not percent abundances. So it's not saying that 1/4 or 24% of it has a mass of 195. It's 24 out of every however many. So you'll see lots of different ways that your abundance can be represented. But when it gives you your values like this, we have to turn them into relative or into percent abundances. And then after we do that, we need to think about how much each of those contributes to the overall mass of that. So very much like you would do your weighted average for your grades, thinking about tests versus quizzes and in-class assignments or final exams versus the trimester grade, the different things contribute to the overall mass differently. Another way we could think of that is if you and your friends bought a whole bunch of pizzas and then you were splitting the cost after, you could either just split the cost totally evenly between everybody, or you could think about if one person ate a lot more than everyone else, then that might contribute more to how much they should have to pay. So the weighted average is taking into account how much that isotope plays into the overall average. So I'm going to make myself, just a little bit bigger here after disappearing so that you can see the math work slightly easier. So what I've done here is just wrote those numbers. If I want to know their percent abundance, I would say for that one, that 24 out of every, and then the bottom is just the sum of all of them, and times 100 to make it a percent, and I've done this ahead of time, 17.1% of my gold has a mass of 195, or 17.1% of my sample is this isotope. Most of my isotope is this middle one, and we can see that. I know that the bottom equals 140 because I've done this a couple times. Over half, and by the height of the graph, that confirms it as well, over half of it is this isotope. The remainder, so we can subtract from 100, or we can do this one last time, 27.9% is the gold that has a mass of 198. So unless it specifically tells you how to round, we're going to be a little bit flexible on that. And very often we'll say to round 1 to 2 decimals when you're doing a problem like this. So those are our abundances as percents. But that doesn't necessarily tell me how much this sample weighs or how much an average piece of gold that is in this sample. We can say, well, the most likely isotope I would find would have this weight. I might find a heavier one. I might find a lighter one. But we want to think about that weighted average, or what would it come out to in terms of an average. It's good to be able to estimate it. Well, I know that this is really abundant. This one's the next most abundant. But this one still has a decent amount, but it's significantly lighter. So one of the skills we're going to do and practice is kind of ballparking this, and we'll do that on number 2 together, but it's estimating and then being able to justify how you did your estimate. And you'll practice that on the virtual lab we'll do as well. But first, we're going to talk about how to calculate the average. So as we're doing that, when we normally calculate an average, we think of each of them contributing equally. I've got 3 things, I divide by 3. But when we do a weighted average, like you would with your grade in a class that has different categories, the different things contribute more or less. So rather than being 1/3, 1/3, 1/3, it might be 50% this and 40% that. Here, 17% comes from this, 55% from this, 27% from this. So what we do is we take our percent, we multiply that by the mass for each of our isotopes, and then we keep adding that up until we have done that for all of our isotopes. That gives us the average atomic mass. And we want it to be in decimal form, so we would put 0.171 times the mass of that isotope, and we're getting that off of the graph. The mass of the isotope isn't how many we have, the mass is how heavy is that isotope, 195. And then the 55 had a mass of 197. The 27.9, that peak to the right, has a mass of 198. You don't have to show each step here, but just so we can kind of go through the process, that right there would come out to 33.3. That would come out to 108.4. This guy would come out to 55.2. And when I sum all of those together, my average atomic mass is 196.9 AMU. And that's cut off there at the bottom, but atomic mass units. So atomic mass units is the unit we use because elements are so light, it's not practical to talk in terms of grams or kilograms or pounds for how much they weigh. So that same work you can check on the answer key, but we are thinking about how much of each thing do I have, and then using the amount that it has, how much it contributes to the overall mass or average weight. In this second one, we have monatomic chlorine. It's going to ask you some questions about this on the quiz, but we also want to talk about how we could estimate this. So as I'm estimating my average mass, I see that I have some with a mass of 35, some with a mass of 37. So my average has to fall between those two. If I had an equal amount of each, the average would be right in the middle, 36. But when you do the math on this, both the answer key and the Canvas questions will tell you that's not right. Because I have significantly more of this isotope than that one, that means that that contributes more or is more important in terms of the weighting. So just like your trimester grade is a more significant part of your overall score for a class than the final exam, this isotope is more of the overall mass than this one. So when we are then about to estimate and justify it, we could make a claim that the average mass is probably around 36.4, 36.5, 36.6, kind of over in this area. Our evidence would be that I have a lot more of the isotope of mass 37 than I have of the isotope of mass 35. And the reasoning would be that the more abundant isotope contributes to the mass much more than the less abundant isotope. So you're going to do that one. You can check your answers. You can also check out the questions there on the Canvas quiz. Here's another one, thinking about, first of all, what happens in our mass spectrometer in terms of deflection, just kind of ballparking our relative abundances so that we can calculate a mass. So if we are going to average this one, we would want to account for that there's a fairly wide spread from 90 to 96. But we see that there's a lot of 90, a lot of 91, and a lot of 92. So if we had to estimate this and think from that same perspective of claim evidence reasoning, a claim would make a lot more sense that our average is in the 91 to 92 range, with the evidence being over half, maybe 2/3, even 3/4 of the zirconium has a mass of 92 or less. The reasoning then being that that contributes much more significantly to the mass than the heavier isotopes, which aren't very abundant. So 1, 2, and 3 are what we do with individual elements. I'm going to pause this video. It's going to continue, but I'm going to pause myself before we go on to the next page, because that's where it talks about multiple atoms bonded together in a compound. We use the same skills, we think about a lot of the same things, but we do have a little bit extra that we are processing as we explain and solve the problems. That was a nice break. As we go on to these next, we're starting to look at compounds. So if we put an atom or a pure element into a mass spectrometer, the mass spectrum that we get is for that pure atom or element. So it would just be individual atoms, and each spike or each peak would correspond to the mass of those atoms. If I put a compound in, then what would happen would be that compound would go through, it would be charged, and it would be bent through the same process, but each of the peaks would correspond to the mass of two of those atoms or three of those atoms or however many of those atoms were bonded together. I said two initially because the first two examples will do have two. So this is the mass spectrum of chlorine gas. So that means a Cl atom bonded to another Cl atom. It says that it shows only the molecular ions or chlorines bonded together, and it's given. Peaks, which are the bars on our bar graph of the mass spectrum, are at the mass numbers of 70, meaning that we have a molecule that has a total mass of 70, 72, a total mass of 72, and 74. When it asks what are the naturally occurring isotopes, that's just its way of saying what combinations of chlorine atoms gave us this spectrum or could make these masses. So it's kind of a process of elimination when it is multiple choice, but we can also kind of strategize and understand what these different numbers might mean. So if I looked right there, a chlorine that is a 35 by itself would give a peak of 35, but if a Cl35 bonded to a Cl35, we would then get a molecule, and that molecule would have a mass of 70. So if the only version of chlorine that I had was chlorine that was 35, then we would get 35 and 35, and we would get one peak that had a mass of 70. As we think about that with 36 and 37 and the different combinations here, we can see how that connects with our graph. To get a peak of 70, we would have to have two atoms that together add up to 70. To get a 72, we need two atoms that add up to 72, and 74, obviously, we'd be two atoms adding to 74. So what I want you to do is take a quick pause of me and think about how can I make these three peaks and no other peaks? If you didn't pause me, you saw me pause myself awkwardly. If you did, then you might have still seen the awkward pause. But what we need to recognize here is as I put these things together, there's different ways of doing it. So if I wanted to make a peak at 70, I would need a chlorine 35. That eliminates D as a good option because there's no way that we can add 36s and 37s together that adds up to 35. When I look at this 74, kind of jumping to the other end, which we'll see is a good strategy, tells me that I need heavier versions, or I need an atom of chlorine that is heavy enough to bond to another atom of chlorine that has a mass of 74. We'll see that that eliminates 36 as the only other combination because a 36 and a 36 doesn't add up to that. We need a heavy enough atom that when I put two chlorines together, it can add up to 74. So we think that has to be 37. So we've eliminated some others. So it can't be A, it can't be B, it can't be D. So we're thinking between C and E. And you might initially, based upon all of our strategies, have been drawn to E right away. Two of these adds up to this, two of these adds up to this, two of these adds up to this, move on to the next one. But the other thing that can happen is in our sample, an isotope doesn't have to bond to itself. A chlorine 35 could bond to another version of chlorine. That is where we can eliminate one answer and prove that the other one's actually a better answer. The right answer on this is C. When I have C, I could take a chlorine 35 and a chlorine 35, put them together to make a chlorine 70. I could take a chlorine 37, a chlorine 37, put them together to make a chlorine 74. I could also take a 35 and a 37, and when they combine, it would give me a chlorine 72. So by using just these two isotopes, I can make all of the different mass spectrum peaks that we see on the graph. Well, why would that be a better answer than this? Because 35 and 35, 36 and 36, 37 and 37, that gives me these peaks as well. But we would also need to account for the fact that what if a 35 bonded to a 36? That would give a peak of 71. On this graph, there isn't a peak at 71. That means that we can't have atoms that add up to 71. There's not a peak at 73. So we can't have a 36 and a 37 because 36 and 37 together add up to 73. We have to have isotopes that add up to all three of these combinations, but only to all three of these combinations. So that's an important piece. Number two uses what we just learned about chlorine. So if you got impatient and jumped ahead, it told you that chlorine was 35 and 37, but we want to use similar strategies. So I'm going to give some tips, but you're going to have to kind of check the answers to get all of the logic on this. So as we think about this, remember that the lightest isotope or the lightest peak is made of either our lightest individual isotope or a pair, a combination of those lightest things. So since this is a Br bonded to a Cl, that's going to be made of my lightest version of Cl, which has a mass of 35, bonded to whatever my lightest version of bromine is. That will help me to figure out what bromine needs to be. The 118 has to be made out of my heaviest isotopes. So the heaviest version of chlorine that's in this sample is a chlorine 37. Well, that has to be bonded to a heavy version of bromine as well. So as we think of that, we would see, well, is the bromine that I had before heavy enough to give me this combination with that heavier chlorine? Or does there have to be a second or third version of bromine? So we have sample examples with 1, with 2, with 3 or 4 different versions of bromine, and we're putting them together with chlorine 35 and chlorine 37 in different ratios and trying to get them to add up to this, this, and this with nothing in between. So the lightest one is the lightest version of bromine to the lightest version of chlorine. The heaviest one's the heaviest version of bromine with the heaviest chlorine. And then all the in-betweens could be from any other version of bromine or chlorine that I would need if more exist. The rest of the questions are just more practice and more support. When we do this on the test, it's really going to focus a lot more on individual elements and mostly what you saw on the first page of this part. So you won't have to do as much with compounds, but it is important that you really stretch yourself, because when you can apply it to compounds and when you really think about what the different peaks mean, in more depth, there will be some that do have just 2 to 3 atoms bonded together, the more simple ones. I'm sorry, I forgot about those. But some of the later ones on this start to ask a lot of questions that have some challenging algebra. So focusing in on these first ones that we went through together is going to get you what you need. Number 3 has a couple isotopes of oxygen. It's asking, when I put it together in sets of 3, so O to O to O, how could those add up to make a peak, or what would their mass be? For all of these, you can check your answers as you're also looking at the Canvas answers. This one right here isn't actually about a compound. It's about scandium. Going to fix the error right there. But on this, it's a little bit trickier of algebra. So think about it as much as you can. Estimate it, ballpark it, and then see, can I solve for this in terms of an equation? If you get a little bit stuck, check the answer key or walk through the strategies that it has in the Canvas assignment. You don't have to solve for one like this, but when you can solve for it this way, that means you really do have it mastered. This one asks us about a molecule of H2S. So it is 2 atoms of hydrogen and 1 of sulfur. And in this case, it's telling us which isotopes we actually have. So instead of figuring out which isotopes, we're trying to see how can I put those isotopes together. The last one asks about Br2. We've seen Cl2, we've seen Cl to Br. Here it tells us about Br2 and asks us to do this and a little bit more challenging of an algebra way, but to understand what the graph would mean, what the peaks would mean, and how we can use that to analyze a sample. So you'll see lots of different things here. If number 1, 2, and 3 on the front and number 1, 2, and 3 on the next page makes sense, those are the main skills. 4, 5, and 6 are all about stretching and going a little bit deeper that you really, really understand it. The lab or the virtual lab that we're going to do is going to practice this again and show it to you so that we can practice these skills even more.